All right, folks. Well, welcome back from this morning. I commend you folks who are who are committing the time to watch these videos in the afternoon as well. Again, I know it's a lot, but I think it's important that we're able to get more time in together, and that way, then we can cover more material. And so, I want to go ahead and I want to finish up with the discussion of photoelectron spectroscopy here, and then so that hopefully tomorrow in our discussion we can go ahead and talk about Beer's law really quickly. And then I just want to wrap up by summarizing the things you'll need to know in Chapter 10 in order for you to take the AP exam. And you'll notice if you quickly take a look at Chapter 10, a lot of that stuff is review, and the stuff that they will ask you on the AP exam regarding intermolecular interactions are about hydrogen bond, London dispersion forces, and also dipole interactions. So a lot of that you know as well. And so we'll start that tomorrow. We'll talk about Beer's law, and then we'll talk about the Chapter 10 material, and I'll finish up over the weekend with a couple of videos that will highlight some of those things for you, and then you'll be ready to go. Okay, so I hope you folks are still prepping and getting ready. Let me know if you have any questions. I haven't seen any of you folks after school. If any of you tried to stop by today, I do apologize. I had a meeting that ran pretty late, and so I wasn't able to get there, but I will be there tomorrow. Okay. All right. Let's go ahead and let's take a look at where we left off with this morning. We were interpreting these spectrum, the spectrum that we were given. Okay. And so you need to be able to take a look at a spectrum, and you need to be able to determine then what the peaks mean, and also how you can use those peaks to understand what they tell us about the atom itself, specifically the location and the number of electrons for the atom. Okay? And so what we did this morning was I gave you the spectrum of the magnesium atom, okay? And I asked you to assign each peak to the electrons that are given to you on the model here. Okay? And so let's quickly use this to review how we interpret the spectrum, and then we're going to practice. You have a homework assignment tonight that's going to give you a chance to practice. I will try to post a couple more practice assignments for you to help you with interpreting the spectrum here. Okay? All right. So with that said, then you will be given these simplified spectra here. So it's a simplified spectrum because it cleans up all the noise. We saw earlier on this morning, you saw the spectra, an actual spectra for the nitrogen molecule, and we saw then that there's a lot of peaks in there. Noises meaning that there's going to be other factors that go in there, and you'll see many other peaks. Okay? And so what the detector tries to do is it tries to eliminate some of that noise. And what we are given here is we are given a very idealized version of the photoelectron spectrum for magnesium. Okay? All right, so with that said, then we see that there are four main peaks. There are four main peaks that show up in this spectrum here. Okay, and so if you notice on the spectrum itself, we have the number of electrons listed for us on the y-axis, and the energy in megajoules, and the energy could be in electron volts, could be in anything. But the energy listed along the x-axis here, with energy decreasing as you go towards the right. Okay? So with that said, then we have a peak here sitting way over here upstream in the up here at about a little bit above about 126 megajoules right here. We have another peak here at about 9.0 megajoules here. We got at 5 and at 0.7. Okay? So remember, the location of the peak on the spectrum indicates then the location of the electrons relative to the nucleus. The closer electrons are to the nucleus, the stronger they are bonded to the nucleus, the more vigorously they're held on to the nucleus because they're closer to the nucleus. Remember, we learned about this. The electrons are negatively charged. All electrons are negatively charged. Okay, so they're negatively charged, and so they are attracted to the positively charged protons in the nucleus. So the closer they are, the stronger that attraction is going to be according to Coulomb's law. So the closer the electrons are, the greater the binding energy, that greater that ionization energy that's needed to remove it. And if you have greater ionization energy, remember we have a lower kinetic energy, particles will move slower. Anyhow, make sure you review that from yesterday's lecture. Okay. And so that means then the binding energy here, that is this energy here, the greater the binding energy, the closer the electrons are to the nucleus. The smaller the binding energy, the further away it is from the nucleus. So the location of the peak on this spectrum here indicates the location of the electrons relative to the nucleus. So again, the further upstream, that means the higher the peak. If the peak is further up on the energy field, and we call it upstream, further up on energy field, that means it represents a larger energy. That means then the electrons are closer to the nucleus. And so we saw then here, the peak here that represents 126 megajoules, okay, those two electrons, those electrons will be located right here, okay, closest to the nucleus. Okay? So the further downstream the peak is, the further away the electrons are. So we saw then that with this particular peak here, it represents the two electrons out here for the magnesium atom. Okay, so that you want to make sure you keep in mind. So the location of the peak indicates the location of the electrons. The size of the peak then indicates the number of electrons at that particular location. And it's all relative here, folks. So some peaks, some graphs will give you the actual number of electrons, others give you relative abundance, but that's not the point that you have to worry about. The point you have to worry about is how are they relative to one another. So if you imagine that, so if you take a look at this here, the peak at 126, the peak at 907, and the peak at 0.74, all those the three peaks there are all the same size, which means that they represent the same number of electrons. The peak at 531, then, if you take a look at this, it's about 3 times larger than this, these two here. So it represents 3 times more electrons. Okay, and so if you can consider then, if we let's go back to this one. If you consider this particular peak here represents electrons closest to the nucleus, what do you think about this? Which atomic orbital is closest to the nucleus? It's going to be the s orbital, and it's going to be the 1s orbital. And remember, with s orbitals, the maximum number of electrons that can be held within an s orbital is 2 electrons, and that's how we were able to deduce then that this peak here represents 2 electrons. Okay, on the 1s orbital, it's the furthest upstream. Okay, furthest upstream represents the greatest amount of energy, which means then it's the closest to the nucleus, and the orbital that's closest to the nucleus is the 1s orbital. And the 1s orbital contains a maximum of 2 electrons, and that's how we were able to deduce that this is 2. So therefore, if this represents 2 electrons, this also represents 2, and that also represents 2 electrons. And if these 3 peaks here represents 2 electrons, this peak here is about 3 times larger. This peak then represents 6 electrons each. And so that's how you're able to deduce then the number of electrons from the peak size. So the peak size represents the number of electrons. The peak location represents the location of electrons, and that's what you have to be able to do in order to determine then read then the spectrum here. All right. So with that said, then if you were not given this, then from that deduction from that there, you realize then that so if you weren't given this diagram here for the magnesium atom, and if you weren't told that this is magnesium, you can go ahead and still write the electron configuration from the spectrum here to identify the particular atom. We did that this morning for phosphorus. Okay, and so let's go ahead and let's write down what we have here. So we have then this peak represents the 2 electrons in the 1s orbital. Okay, the next peak over then, once the 1s orbital is filled up, this peak then must represent the electrons in the 2s orbital, same size, next energy level up, 2s orbital. This peak here then must represent the 6 electrons in the 2p orbital, and then this peak here must represent the 2 electrons in the 3s orbital. So you have to remember then, go back and review the ordering of the atomic orbitals in order to make sure you are able to fill these out. Okay. All right. So again, make sure you understand we're not going to examine photoelectron spectroscopy for molecules. Yes, we have been talking about molecular orbitals. But we're going to focus it on just taking these photoelectron spectrum for atoms, and interpreting those, because they're a little bit simpler to identify and to interpret and to read than the spectrum for molecules. Okay. All right. So let's go ahead and let's practice this. Let's practice this here. Okay. So let me give you a let's do this up here. Let me give you a spectrum. Okay, and ask you to interpret. Okay. So take about 2 or 3 minutes here, folks. So this is the spectrum here that's given to you. Okay, this spectrum here has 5 peaks. It has 5 peaks, and remember, each peak represents a unique set of electrons. So you have 5 sets of electrons here. Okay, look at the downstream. We have the relative number of electrons here, and we have downstream, upstream down this ways. We have a peak here, the 2 peaks midway through, and the 2 peaks here. Okay, so what I would like you to do, take about a couple of minutes, and you tell me based upon this photoelectron spectrum, okay, what is the atom? Okay, so this is an atom. Let's interpret this atom here. Okay, let's go ahead and take a couple minutes to get that done. Okay, let's go ahead and let's interpret this here. Okay, so first of all, then, whatever this atom is, we don't know any clue. We don't have any clue about this atom here, but we do know this. We do know this, and let's go ahead and indicate what we do know. We know then that this peak here represents a unique set of electrons. So do each one of these peaks here. That means we have 5 separate locations. We're examining electrons at 5 different locations. The one furthest upstream here, will be the orbital closest to the nucleus. And what is that orbital that's always closest to the nucleus? This orbital then, now let's go ahead and write this in, that orbital then will be a 1s orbital. So moving upstream then, that means that this particular electron, so this peak here represents the electrons in the 1s orbital, and so this peak here must represent the electron in the 2s orbital. This peak must represent the electron in the 2p. What's after 2p? 3s. So this peak here represents electrons in 3s, and this peak here represents electrons in the 3p. 5 different locations. So there are the 5 different locations here, with this one being the closest to the nucleus, this here representing electrons furthest from the nucleus, because it is the lowest in energy. It's the furthest downstream. This is the furthest upstream. Okay. All right. So if this represents the electrons closest to the nucleus in the 1s orbital, how many electrons will we have here? What's the maximum number of electrons that can fill in a 1s orbital? 2. Okay. And so that means then this peak here, the peak at the 2s and the peak at the 3s, they're all the same size, which means that each one of these represents then 2 electrons as well. Okay. All right, so that's what you need to do, folks. Like I was telling you, the more you do this, the easier it becomes. And the reason why we learn about photoelectron spectroscopy at this level here, because it is so easy to interpret. Okay? All right, so let's go ahead and let's take this peak here that's just upstream from the 10 megajoules here. Okay, so it appears then that this particular peak is about 3 times larger than this one here. Okay, so which means then this is going to be 3 times 2 would be 6 here. Okay, so that's what we have there. Okay, and so this is 3 times larger. You can see then this last peak here, it's not quite 3 times large. It's not twice as much. Okay, so it's about 2.5 times larger roughly. And if it's 2.5 times larger, then you can imagine that this represents a 5 electron. Okay? And so that's how you go about doing this. So what is the electron configuration then for this atom, whatever it is? Let's go ahead and write down what we have. The electron configuration then is going to be, let me go ahead and write it here, 1s2, 2s2, 2p6, 3s2, and 3p5. Okay, so that's the electron configuration for this mystery atom here. And so how do we identify what the atom is? Folks, going back to what we did in first year chemistry, add up the exponents here. So we have 10, 15, 16, 17. Okay, and so let me just check my periodic table here really quickly. Okay, so the atom that has 17 electrons, the neutral atom that has 17 electrons, then is going to be chlorine. So this is the electron. This is the photoelectric electric spectrum for chlorine. Okay. All right. Very good. So that's how you go about doing this here, folks. And so let's go ahead and let me go ahead and save this for you quickly. Let's go ahead and let's identify then. So this is the spectrum for chlorine. Okay. So there's the photoelectron spectrum for chlorine. Let's go ahead and position. Let's find the position of each one of these electrons here. Okay, so this peak here represents, and let's go ahead and draw that, these electrons here at the 2s orbital. Okay, let's go ahead then, let's continue with identifying them. And then this peak here then will represent, and we'll just arbitrarily choose 2 here. Okay, this peak here represents, let's say, these 2 electrons here at in the 2s orbital. Okay, and so therefore this third peak here, and let's go ahead and draw that, this third peak here will represent the 6 electrons here, let's see, that's 2, 4, and 6. There. Okay. So this peak here represents this this set of electrons here, here, and here. Okay. Let's go ahead and continue with identifying these electrons here. So then this peak here will represent then the to say these two electrons there and 3s orbital. Okay, and then finally let's go ahead then and let's identify the last peak here. The last peak here. This peak here then represents those two, and that one to make 5, and that's where we find all of our electrons. Okay, so make sure you're able to do this, folks, and identify these electrons here. But I think it's the important skill is being able to recognize, first of all, that this is going to be chlorine. Okay, all right, very good. Let's go ahead then. Let's continue on with our analysis here. Okay, all right. So we've looked at the photoelectron spectrums for individual atoms. Okay, we can actually use we can put two spectra on two atoms on a single spectrum and use that to identify the atoms themselves. Okay, so here we have hydrogen and helium. Okay, so let's go ahead then. Let's take a look at how we can identify this here. Okay. So I've told you here that this is the photoelectron spectrum for hydrogen, and then this number of electrons here, and this is the photoelectron spectrum for helium. So let's go ahead and write this in. This is for helium right here, and this is for hydrogen. Let's go ahead and analyze this for both atoms here. Okay. All right. First of all, let's go ahead and let's look at the size first. The size of each one of these peaks first. Okay. So it looks like here, the size of the peak here is about half of this one, which makes sense because the hydrogen here has 1 electron in the 1s orbital. This says helium has 2 electrons in the 1s orbital. So there it is. That kind of makes sense. The size of the electron, the size of the peak kind of accounts for that as well. Okay. All right. Now the question though is, why then does the peak for hydrogen, the peak for this 1 electron for hydrogen, appear further downstream than the peak for helium here? Okay, why is that the case? Well, let's consider what we have here. Let's remember, the location of the peak represents how close the electrons are to the nucleus. That's what we saw in the previous slide. Okay, but here we notice the 1 electron here is in the 1s orbital, and the 2 electrons here are also in the 1s orbital. So why wouldn't they be in the same place? Why wouldn't both peaks appear in the same place? So there has to be a reason why the helium peak shifts further upfield than the hydrogen peak. Okay, and so let's go ahead. Let's draw out what we have. Okay, let's draw out what we have. We know then that the 2 electrons here. Let's draw out the helium atom. The helium atom has 2 protons sitting in the nucleus there. Okay, and the 2 electrons float around outside here in the 1s orbital. So there are your 2 electrons there. Okay, hydrogen, so this is helium. Okay, hydrogen on the other hand has 1 proton in the nucleus, and it has 1 electron sitting out here in the 1s orbital. Okay, and so why then do you think? Why do you think? So I would like you to real quick on your paper. I know you don't have to submit this, but on your paper, why do you think then that this, what accounts for why this peak here shifts downfield? And remember, what this this upfield shift is pointing out is that these 2 electrons are held more tightly to the nucleus. Now, we had talked about how if the electrons are closer to the nucleus, they're held more tightly. But is there another factor that we can use to account for why the electrons are held more tightly? Because here, both electrons are at the same place. The electrons here and the 1 electron here, they're both sitting at the same location in the 1s orbital. So why is it then that these 2 electrons take more energy, require more energy? Their binding energy is greater, which means that it takes more energy to remove. The binding energy here is greater than the binding energy for these electrons here. Okay, consider that. All right, let's go ahead and I want to consider it using Coulomb's law. Let's go ahead and determine then Coulomb's law. Remember, Coulomb's law then is going to be, this is not Planck's constant. Go ahead and use that really quickly. It's Coulomb's constant. Okay. Coulomb's constant, charge over r squared. Okay. All right. So with that said, then the distances here, and remember this gave us the energy for each electron, and we talked about that. And so with that said, then the two charges here, okay, the distances are the same. Okay, the distances are the same. That electron is a negative charge, and then the protons here is a positive charge. But the key difference here now, is that the proton, helium has two protons, that it has twice as much positive charge and it has twice as much negative charge. And so the attraction here, the binding energy, the attraction for these two electrons, for those two protons will be greater than the attraction for this one electron for the one proton in hydrogen. Now, you can argue then that there's a repulsive effect here, which you would be arguing correctly, but that repulsion there does not overcome the attraction that these electrons have for two protons rather than just one. And that's how we can account then for the upfield shift of the two helium electrons as opposed to the one hydrogen electron here. And so comparing the two peaks here, we can now account for why we have a shift for these two electrons further upfield than these electrons here, okay? All right, so please make sure you consider that, because that's something that, again, I think your book is a good book and I chose it for a reason, but it doesn't do a very good job of covering the photoelectron spectroscopy and all of the little details that come up with that, okay? So in answer to my question is that, here, helium has more protons, and that's because of that, the electrons here that we see on the photoelectron spectrum is shifted further upfield than that of the hydrogen. Okay, so I've run out of time here. So what I'd like to do then is tomorrow I want to go ahead and continue interpreting photoelectron spectrum with two peaks, two or more atoms on them, and use them to interpret the spectrum. So please make sure you take a look at the homework for tonight. Okay. And then tomorrow we'll get together, we'll meet, and we'll finish up this year. And my hope is that we can talk about Beer's Law tomorrow as well. Okay. All right. So very good, folks. Thanks for joining me this afternoon, and have a good rest of your day. And I will see you tomorrow. Okay. Have a good day, folks.